Thank you. Yeah, so apologies to the organizers. I decided to talk about something different than what was advertised, but it's something that is pretty recent and I think maybe top of my mind, so sort of have anxious to share it with everybody. So, okay, so the title of my talk is Spin-orbit coupling and orbital magnetism in crystalline graphene. So I want to start by just telling you a problem that we've been puzzled by for the last couple of years. So, without giving too much background, in Bernal bilayer graphene, which is a very commonly studied allotrope of carbon, right? It's just two layers of graphene stacked in the same stacking order that they appear in bulk graphite. If you study using here's transport measurements, this material when you've made it clean and so on as a function of carrier density and applied perpendicular displacement field, then you find a curious transport phenomenology, which is that at zero magnetic field, there are some magnetic phases, which I'll get back to, but there's no superconductivity. But if you turn on a large in-plane magnetic field, then a small region of the phase diagram becomes superconducting. Now, these are systems in the very clean limit, and as of when we were doing this, to our understanding, there was no spin-orbit coupling, so we really didn't understand what was going on in these systems. Okay, but superconductivity is very nicely developed. TC is quite low, 30 millikelvin, but it's very clearly a triplet superconductor. So it's a clean limit. You have a TC of 30 millikelvin. Actually, superconductivity doesn't start until Zeeman energies about the Pauli limit or a little larger, and then it continues to several tens of times the Pauli limit, limited only by the size of the magnet that we had at the time, as far as we know. Okay, so you have some triplet superconductor. It doesn't happen at zero magnetic field, but it happens in a finite magnetic field. Okay, and it seems to have something to do with a competing phase. There's a resistive phase in the same region of the phase diagram, which has its own curious properties. It has some threshold nonlinear transport. It looks a bit like a charge density wave if you're just going from like monkey brain pattern recognition in terms of the transport phenomenology, but the point is that it has some threshold nonlinearity, and it doesn't superconduct, but it's just some metallic phase. Okay, and we did not know what this was. Okay, so the puzzle is basically, why does B parallel stabilize superconductivity in Bernal bilayer graphene? Why is there no superconductivity at zero magnetic field? Okay, this is, again, it's difficult to understand because it's an atomically thin two-dimensional system, and actually it's even more atomically thin than you think. It's a bilayer, but these experiments are done in a limit of extremely strong electric field so that the wave functions are basically 90 or 99% polarized onto one layer. So it's really like you can think about it as a monolayer system. So there's really no orbital effect of B parallel. It's really only a spin effect, and spin seems to be playing an important role. I think, as Steven is going to tell you in a talk later this morning, if you introduce some spin-orbit coupling artificially, actually this phase diagram changes dramatically, and you get tons of superconductivity with a TC that's 10 times higher. You'll hear more about that. But the basic point of this talk is that you need to understand the spin physics if you want to understand this pretty strange phenomenology. Okay, so to give some sort of basic background on the sort of underlying electronic structure of these systems, I'm going to be showing you actually mostly data on ABC trilayer graphene, but all of these rhombohedral multilayers are very similar in their band structure, certainly in their symmetries. The interlayer hopping between layers basically takes the three sets of or n sets of Dirac cones from these layers and gaps out all of them and leaves something that, in the very simplest picture, is a quadratic or third degree or fourth degree band touching, but in sort of the full tight binding calculation, you basically have these band edge or really saddle point Van Hove singularities happening just at some relatively low density. And this depends on the number of layers, the precise details, right? But they all are more or less similar in that regard. You have some saddle point Van Hove singularities and this trigonally warped band structure at low density. And as you dope these systems, here's now transport data from ABC trilayer graphene. You see a kind of a similar, but different in the details, but similar conceptually phase diagram. You have magnetic phases, which have different resistances, but then you have a variety of superconducting phases right at the boundary of some of these magnetic phases. Okay, and some of these superconductors in ABC trilayer are Pauli limited. Some of them are, again, triplet, exceeding the Pauli limit by some huge margin. No change in TC as you make the in-plane magnetic field or the Zeeman energy many multiples of TC.
So what is the color scale here?
Color scale here is resistivity again. So bright blue is basically zero resistance, and then darker blue and yellow is totally insulating. Yeah, sorry, that's missing a plot, the same as previously. Okay, so I'm going to show you basically a set of data from the different experimental tools that we've tried to bring to bear to understand this problem. Okay, so our basic setup looks like this. We have a dual-gated ABC trilayer device. We can control the density and displacement field. I've been showing you transport data taken in this geometry. Then we also have a charge sensor attached to one of the gates. That's basically a transistor amplifier that lets us measure the electronic compressibility by looking at the modulated charge on one gate as a function of a modulated voltage on another. And then we have a nanoscale superconducting quantum interference device, which we can bring just over this gate and look at the local magnetization. Okay? So to give you examples here, right, this is what compressibility looks like over a similar range as I just showed you transport. So this is electronic compressibility. Here, yellow means insulating. That's what happens at charge neutrality. Blue means negative. So you have negative compressibility, which separates regions, which, as I'll show you, are all first-order transitions in which the magnet, basically the spin and valley polarization of the ground state is changing. Okay, you can use, of course, transport and quantum oscillations to sort of count the number of Fermi pockets. And what you find is that there are regions of the parameter space where you have only one Fermi pocket, so you've lifted the spin and valley degeneracy. You have regions where you have two. You have regions where you have four, so you can have half metals and quarter metals. And then you can have a whole slew of complicated phases that have to do with Lifshitz transitions and so on, and pneumatic transitions and so on. But what I want you to remember from this is that, from our previous studies of the system, the things that we have understood are the following. First of all, exchange physics is strong, so this is basically a Stoner-type system. But there's also a Hund's coupling, which really favors spin-polarized phases. That's going to be very important for spin triplet superconductivity. So in other words, there's some microscopic interactions which prefer the system to be spin-polarized rather than, for example, valley-polarized under, when you might nominally have near degeneracy between those phases. Okay, so we can try to compare, for example, inverse compressibility and transport. Here's transport, here's inverse compressibility. Sorry, I lost the color bars again here, but this is inverse compressibility and this is transport. Superconductivity happens at the boundary of some change in isospin polarization. But if we look at this closely, actually, originally we thought, oh, this might have something to do with magnetic fluctuations. I can't exclude it. On the other hand, if we look very closely at compressibility here in blue and superconductivity, we find that superconductivity is actually happening right on the boundary of a first-order phase transition. There's a discontinuity in the, in the free energy across this phase transition. Okay, so maybe this is a competing order scenario is maybe more relevant. PIP is partially isospin polarized. So this one is completely symmetric as far as we can tell. And then this one is partially polarized into 2 out of 4 flavors, but it's not a full half metal. This legend is just sort of schematically, these are 4 annular Fermi surfaces, right? 1 for each spin valley flavor combination. So here you have 4-fold degeneracy, and the Fermi surface topology is that you have an annulus. Okay. All right. So let's see what it looks like in NanoSQUID on tip microscopy. So these sensors were pioneered by Elie Zeldov and his group. They're these tiny little squids. We've made some improvements recently to improve the sensitivity, so we can now relatively routinely do about 1 nanotesla per root hertz imaging, which corresponds to a spin sensitivity of well under a Bohr magneton. And I'll be showing you experiments taken at 300 millikelvin, which is sort of in the range, and with vector magnetic fields, which is in the range of all of this physics. Scale for frequency is kilohertz. Yeah, kilohertz. So this is what gate modulation imaging looks like. So basically what we're going to do is sit along, in this case it's a particular transition in an orbital magnet, so you're going from having no orbital moment to a finite orbital moment, and then you can scan around in real space, and this is what our ABC trilayer looks like, right? And so this is essentially giving you a picture of the change in magnetization as a function of a small modulated gate voltage. And we can look at the whole phase diagram of ABC trilayer, and you can see that magnetically, just as it is in transport and capacitance, it's extremely complicated. There are many different competing phases. Okay, for the remainder of this talk, though, right? It's okay. So the basic picture is we're going to try to use this kind of stealing this from something that Edward Snowden, I think, made us aware of at some point. Like, we want total information about the system as much as we can. There are many things we can't do in van der Waals heterostructures. There are many techniques that are not available, but there are some that are, and here, it's really a combination of transport and thermodynamics. But for what I'm going to show you in the rest of the talk, basically we're just going to focus on a tiny little piece of this phase diagram where we can actually understand things well. There's tons of things we don't understand in these phase diagrams. I don't want to sort of oversell our level of understanding, but there's at least one tiny corner where we think we are able to isolate some microscopics and really understand what's going on. And that's the regime of this quarter metal. So basically we're going to focus on a regime of the phase diagram where quantum oscillations show a single, simply connected Fermi surface, which just corresponds to occupation of 1 out of 4 of these spin and valley flavors. Okay? And the sort of first statement is that there are actually 2 such phases. Okay, so if you look here, there's this red region in compressibility and then another region that has nearly the same compressibility. So they both occupy 1 out of 4 flavors. Okay, but they're separated by a dip in compressibility. That's our signature of a first order phase transition. Okay, so what are they? I'm going to try to convince you that one of them corresponds to condensation into 1 valley and the other corresponds to coherent superposition of the 2 valleys. So you have a valley imbalanced phase and an inter-valley coherent phase. Okay. Wait, just a little. Okay. Yes, but okay. Okay. So the one way to see this. So I'm gonna show you data now taken with a large in-plane magnetic field because I don't want to think about the spin. So let me polarize the spin completely. Okay. And this valley imbalance phase and this inter-valley coherent phase. Here's the first order transition that separates them. If I look at NanoSQUID measurement of the local magnetization, you basically see that this is you can think about this as a derivative of the magnetization along basically a horizontal line. Okay, as I enter the valley imbalance phase, I see that it has a finite orbital moment, so magnetization goes up, so it's large in this phase, but then as I go into the inter-valley coherent phase, it goes down again. Okay, that's because the valley imbalance phase has a large orbital moment, and the inter-valley coherent phase has no orbital moment. Okay, this is sort of keeping the spin polarization fixed by this large in-plane magnetic field. Yes.
What do we understand concerning this first order transition? Since you have the density on the horizontal axis, should we understand that you have some region where the system becomes somehow like in a liquid-gas transition, inhomogeneous, and you have to make a Maxwell construction separating?
So in principle, yes. I think once you have gates, all of this Maxwell construction physics is like restricted to a tiny narrow range. Yeah. So I don't think there's a very wide range of phase coexistence, but in principle, yes.
Okay. Andrea, very quickly, about inter-valley coherent state. Yeah. You said, during the last phrase, you said spin is not involved. How can you get splitting 1 to 4? I mean, how can you get
so our picture here, okay, so the picture here, along the lines of Subir was asking also, is these are both spin polarized phases, right? And then one of them is valley imbalanced, fully condensed into 1 valley. One of them is inter-valley coherent, equally spread between the 2 valleys. Okay, it's not the only thing that can happen, but that is what happens right here. Okay, so you can actually confirm this just from transport experiments. What you're looking at here is transport as a function of out-of-plane magnetic field, and this is the transition between the valley imbalance and inter-valley coherent phase. You see that the valley imbalance phase gains parameter space as a function of out-of-plane field. Makes sense, it has an orbital moment. The IVC phase loses it relative to the valley imbalance phase, but it actually doesn't change relative to actually just an unpolarized paramagnetic phase. So it has no orbital moment as far as we can tell, certainly no more, not detectably more so than a simply unpolarized phase, and less than the valley imbalance phase. Okay, so that's telling you that it basically has 0 orbital out-of-plane moment. And if you want to do, beat this horse even harder, the valley polarized phase has a large anomalous Hall effect, whereas the inter-valley coherent phase has no anomalous Hall effect. So it really looks like one of them is an orbital magnet, one of them has no orbital magnetization. Okay, so far so straightforward, right? This is something that was basically expected. Inter-valley coherent phases have been seen in graphene quantum Hall and twisted bilayer graphene and twisted trilayer graphene. It's a natural thing to happen in these systems. It seems to happen relatively ubiquitous, so it's not so surprising that it also happens in, these crystalline graphene systems at finite density. The puzzle is actually has to do with the susceptibility of these phases to in-plane magnetic fields. So in principle, in our naive picture, these are all totally spin polarized phases, and actually that's a very reasonable thing to assume. But when we look at the in-plane field dependence of this phase boundary between the inter-valley coherent phase and the valley polarized phase, we find that they're quite different. In particular, it looks like at low magnetic fields, the inter-valley coherent phase has a much larger susceptibility in the plane, and the valley polarized phase has a much smaller susceptibility. However, at relatively small fields of a Tesla, these saturate. Okay, so I was showing you data before from this region where it's a simple transition. Actually, at lower fields, there's actually multiple transitions and intermediate phases and so on. Okay, and this doesn't make too much sense because if you don't have spin-orbit coupling, and spin-orbit coupling in graphene is thought to be very weak, then basically spin is a good quantum number. And in any magnetic field, you should just polarize the spins in the plane. There's certainly, you expect both of these phases to be totally spin polarized. So they should have the same divergence susceptibility, and you should see no change in this in-plane susceptibility. But it doesn't look like that's the case. Okay? So basically what we think is happening is as follows. There's indeed spin-orbit coupling in graphene. We just never like to think about it, but it's there. Okay? It's Kane-Milli type. As a note, in the situation that we're considering, which is large electric fields, which polarize the layers, this is the same as Ising spin-orbit coupling. Actually, the sublattice structure really doesn't matter because you polarize the sublattices. Okay, and we know that adding spin-orbit coupling from a substrate at the 1 MeV level has a pretty big effect. That's Stefan's talk later, I think. But what about intrinsic spin-orbit coupling? Well, theory estimates range very widely. Kane and Milli originally estimated 2.4 K, but I think they wanted it to be really big. Later there were estimates at 10 or 15 millikelvin, but maybe those people wanted to be really small. More recently, it's sort of somewhere in the geometric mean of those two. Okay, it's, it's apparently not so straightforward to calculate it. Certainly, I've always had in my mind that it's just something negligible, but as I'll show you, I don't think that's in fact correct. So actually, the physics that I've shown you is very naturally explained by a rather moderate size of Kane-Milli spin-orbit coupling. Okay, so the picture is as follows, which is that if you just think about a rigid IVC, just assume that IVC is fully polarized, there's no valley imbalance, then it doesn't see the spin-orbit coupling because it's inter-valley coherent. It has the same spin on the in the two valleys, but that is just going to have zero expectation value with the Kane-Milli. Okay, so it doesn't gain any energy, but actually a valley polarized phase does gain energy. It's all in one valley. It can choose to align its spin either, in the direction favored by spin orbit for the particular valley that it's in. So as you turn on spin orbit coupling, the valley polarized phase will actually win a little bit of energy. But now if you turn on an in-plane magnetic field, the spin valley locked phase, which is the valley polarized phase, is spin valley locked in a way compatible with spin orbit coupling. It's only going to gain quadratically from the in-plane magnetic field because it has to fight spin orbit. So you need to push it, you need to push spin orbit to the point where it's no longer important by polarizing the valley balanced phase the valley imbalanced phase into the plane, and whereas the intervalley coherent phase can just polarize in the plane. And so this is exactly, the fact that these two lines, this is energy versus in-plane field, eventually become parallel is precisely that saturation of the difference in moments. Okay, so that's what you see here, right? And it turns out, we're kind of dopes. We should have known this beforehand. There's actually a bunch of experiments which, in very different contexts than graphene, which find spin-orbit coupling, in the range of half a Kelvin. Okay, and indeed, if you just ask what spin-orbit coupling is required to give you a saturation around half a Tesla, of course, it's just half a Kelvin, roughly, right? So we never thought about this. Nobody ever thought about it, as far as we can tell, in the context of twisted bilayer graphene or other carbon systems. But this is actually not an insignificant energy scales when it comes to the minute energy differences between different correlated phases in all of these graphene systems. Okay, similar physics for electron doping I'm not going to talk about. Okay, so just to wrap up, let me sort of tell you what we think this means for triplet superconductivity in these systems. Okay, we see triplet superconductivity in half metal type phases. They are generally valley unpolarized but spin polarized. Okay, so what's the effect of superconductivity in those phases? There are basically two options that we can think about. One is where basically this Hund's coupling is sufficiently dominant that the spins do polarize in plane, but then they will cant a little bit because they can gain a little bit of energy. They'll lose some Hund's energy, but they will gain spin orbit energy by canting a little bit out of plane in the two valleys. So you still have balanced Fermi surfaces, and that's not pair breaking for a triplet superconductor. On the other hand, there's this other option where you, instead of canting the spins, you actually polarize them out of the plane, but then change the size of the two Fermi surfaces. That is pair breaking, okay? The difference between those two is determined by some interplay of how strong is Hund's, but also then what is the density of states. If you have some very large density of states, it doesn't cost much energy to depolarize, to basically create a net Valley moment in this half metal. And once you create that net Valley moment, that's basically a pair breaking. Now, what we think is happening in Bernal bilayer graphene, then by extension, is that we are in this latter scenario where at zero magnetic field, we have a finite Valley moment, okay, because that's the regime that we're in. It has to do with just what's the density of states for that particular phase. How much does it cost you? What's the Valley polarization susceptibility? But then when you put an in-plane magnetic field, you eventually overcome spin orbit. You cant the spins into the plane, and once they're in the plane, they no longer Valley imbalance because there's no spin orbit. They don't see spin orbit anymore, okay? So that's a nice story. Is there any evidence for it experimentally? This is the best I can do. It's not perfect, okay? But I'll remind you of this threshold nonlinearity, which we saw, okay? So I said it looks like a charge density wave, and that's true, but it also looks like something else which we actually see in these systems all the time, which is domain dynamics. Okay, now we are not able to measure it here because this is all very low temperature effects, which are beyond where we can look with the SQUID, but we have done a similar experiment in ABC in this Valley imbalance phase. So here I'm showing you current versus nonlinearities in the current, right? There's this threshold nonlinearity that happens in this competing phase before it becomes superconducting, but in ABC trilayer, I've just shown you this competition between Valley imbalance phases and inter-Valley coherent phases, and the Valley imbalance phases also have an identical threshold nonlinearity. These are at higher temperature, and I'm basically done. And so we can image them, and so here here we're looking at these threshold nonlinearities and simultaneously doing magnetic imaging, and we basically see that the threshold nonlinearities are associated with magnetic domain dynamics. It's where you nucleate a new domain with opposite Valley polarization, which we think is coming from as in TMD systems, some interplay of spin Hall and Valley Hall and destabilizing, the ground state magnetic order. So basically, the picture that we have now is that spin triplet superconductivity is suppressed in some of these systems because spin orbit coupling is pair breaking. And you can suppress spin orbit coupling by putting large in-plane magnetic fields, which then basically remove the effect of spin orbit coupling, restore Valley balance, and restore the right symmetry to give you superconductivity. So since I'm out of time, I want to leave some time for discussion. Let me fast forward to the most important part. So let me acknowledge, this was work that took a very long time to work out over several generations of graduate students. It was started by Haushin, Zhou, but has been finally brought to conclusion by Trevor and Owen, and many other contributions from people in my group. Let me acknowledge Erez, who's here, who's helped really crystallize some of the understanding here, and of course Takashi and Kenji for making this all possible. So, thank you.
Yeah, thanks a lot, Andrea. Questions, Andre? Over there. Yes.
Is there any dependence on the angle of the magnetic field in the plane?
No. We spent a lot of time for a zero signal there. Not as far as we can tell. If it's there, it's extremely weak. Yeah.
Yes.
Andrea, if possible, very quickly, to sort of questions, sort of comments. One is that with Leonid Levitov, who is here, we looked into superconductivity in this material. And what you said is wonderful, but there is another issue, repulsion versus attraction. And in the scenarios that we have, without going into details, there is a magnetic field-induced superconductivity, but it acts in parallel with Ising spin-orbit coupling. So there is no competition. And
okay.
I'm wondering whether one can distinguish.
I know your paper, but I had not appreciated that fact. Yeah.
And second one is about the Valley polarized state. Again, sorry, there are 4 people in the room who worked with me on this Valley polarization, and our scenario is again different from what you are saying. We are saying that the phase which you call Valley polarization is ferromagnetism in one valley and simultaneously Valley disbalance. So it also gives splitting 3 to 1, so there is one water metal.
How different is that? I mean, I think
the ferromagnetism only in one valley, not in both valleys.
in one valley.
Yeah. not in both valleys. Okay. And I'm wondering again, is there an experimental way to distinguish between fully polarized state and the state which is polarized only in one valley?
You're talking about the competing phase for Bernal. The zero field phase is what you're talking about, or you're talking about?
It's about zero field. It's about the phase which you call valley polarization. You said that this phase is fully spin polarized and in addition has valley disbalance. Density of two valleys, so it's not the same.
There's at least one, okay, there's one scenario in ABC, which is one Fermi surface in one valley, fully spin polarized, and that, I will die on that hill, is indeed what
and
is
this
there,
is
right?
the same as I said.
Okay.
Ferromagnetism in one valley and simultaneously valley polarization. It gives you exactly the same.
Okay, okay. If that's the case, then,
yeah, I'm just wondering
then,
whether there is any way to experimentally distinguish between.
Maybe we should talk about it afterwards because I don't actually understand what's different.
Yeah, sure.
Sorry. Yeah.
I'm here. So I also have some comments and questions mixed together. So one thing is, do I understand correctly that superconductivity occurs near this phase separation regions? Is this something?
Sometimes yes, but not always.
Okay, because this is somewhat reminiscent of what we found many years ago in the context of cuprates, where a strong correlation often induced when you have also some attractive forces from phononic or magnetic origin, phase separation. And near the spinodal line, you find a very strong attractive forces which can induce S-wave and also D-wave superconductivity. So I was wondering whether this occurrence of superconductivity is related to some spinodal region around this first order transition.
I think probably the clearest refutation of that as a general mechanism is probably, again, you'll hear from Stefan, because sort of small tweaks, like adding some extra spin orbit, make entire phases far from phase transition superconducting. Mm-hmm. And so, yes, superconductivity happens near phase transitions sometimes, but they're generally first order, but it also happens not near phase transitions, depending on details. Okay. So it doesn't seem like a universal feature. Okay.
Another question is related precisely to spin orbit issue, because spin orbit is also related to local magnetic fields, which could be self-consistently induced by the density, which is not homogeneous. So sometimes you might even think that some spin orbit is created by some relative abundance of carriers there, which are also attracted there because the electric field induces a farther, stronger spin orbit. So this is another mechanism which could induce and help phase separation and attraction.
So let me just not answer your question directly, but answer with just an empirical fact, which is that the density inhomogeneity in these systems you can measure in various ways, but among them you can tell how sharp are some of these phase transitions, for example, in capacitance, and you could compare that, actually it's sort of in this data, to the range over which superconductivity occurs. And superconductivity can occur over a much larger range. This is the first order phase transition. This is how sharp it is in density. Superconductivity happens over several times larger here and maybe 20 times larger in
but the residual attractive tails can be extended.
Yeah, that may be, okay. Yeah.
And thanks for the fantastic talk. Just out of curiosity, I'm far from that field, but it sounds to me that from symmetry, could you also do something similar with an in-plane strain, that you could break the symmetry between the valleys that way? And would you expect then also to induce superconductivity?
There's a few questions in that question. Yes. I think it wouldn't be the same. Could you induce superconductivity? Yes, surely, because everything seems to induce superconductivity in this system. So I imagine that would lead to some new superconductors in some interesting way. But it wouldn't, I think at least my understanding here, which clearly not everybody in the audience agrees with, is that the basic point here is to have spinless time reversal symmetry. And when you have that in a kind of spin polarized half metal, then it seems reasonably likely for it to superconduct. Depends on a bunch of details of the Fermi surface. Strain doesn't, may or may not impact that. Depends on what other symmetries are also broken. Yeah. That's right.
Yeah. Hi. You must have said it, but I probably missed it. So you think that spin orbit isn't used by the substrate?
No. Spin orbit is there all the time.
So it's
intrinsic graphene spin orbit. Yeah.
So there was.
Then you can also induce it by the substrate and make it much stronger. But yeah, that's not the.
So there was an ESR a couple of years ago by Blick.
Yep.
I think they measured 40 40 millikelvin.
Yeah, I think that was Sichao.
Yeah, yes.
This
Sichao,
reference,
yes,
yeah.
yes. Okay. Sorry, 490. So are consistent with what you're seeing?
These are all kind of in the same range of, hundreds of millikelvin, yeah.
Right, but is it enough to produce the effects that you...
Yeah, it's quite consistent with the curvature of this. I mean, maybe here we get 700, but on the this is a little bit convolved with some many-body physics, and there's some experimental uncertainty. I think these are all pretty much, they're all consistent to within a factor of,
And your substrate is made of what?
Hexagonal boron nitride.
Okay, so you wouldn't expect any...
Would not expect effects from that.
So Andrea, let me ask you a question from a much higher level. I was not going to ask you a question, but as you said, not only in the talk that you gave, everywhere in graphene there is superconductivity. Twisted bilayer graphene has superconductivity. Barnol has superconductivity. Trilayer graphene has superconductivity, varying from 2 Kelvin all the way to 20 millikelvin, right? So should I think, and I of course have a viewpoint on it, I thought it's all electron phonon, I'm not so sure anymore. Okay, it's, so should I think of each of them as a totally different system, right? And totally different mechanism, or do you think there is an underlying overarching mechanism here? I mean, I'm asking your field.
Now we're getting like aesthetic, it's an aesthetic preference that I have, which is to say they're definitely all the same thing.
Good.
But it turns, as you well know, it's very hard to kill anybody's theory of superconductivity with experiments. So,
if it's all one mechanism, I just don't see how it can be anything other than electron phonon. But that's of course a bias. Bias based on actual.
I'll let the audience. Let's open this up for discussion. I'm sure we'll find some disagreement here. Right?
Last question.
Yes.
So can you tell us what do you mean exactly by quarter metal? I gather that it is about valley polarization.
Valley and spin polarization. Yeah.
So how can you said that you can detect it by comparing quantum oscillations with, so can you just briefly say how does it work?
There are two, so quantum oscillations, sorry I didn't get a chance to go into this in detail. Quantum oscillations in the simple quarter metal regime simply show that there's one Fermi surface that is 100% of the Luttinger volume. Okay? So that's what I mean by detect by quantum oscillations. You see one peak and it corresponds precisely to the density. In normal graphene, you see one peak that corresponds to a quarter of the density because you have 4 Fermi surfaces for each spin and valley flavor.
Since the valleys are degenerate, the size of the orbits are the same. How can you distinguish between?
No, they're not the same because we know the density.
All right, thank you very much. Good to see a lively discussion. So the organizers told me we have like 5 minutes more for the discussions than scheduled. So it's nice to use that.
That was not mine. No, this.
So thanks, Andrea.
KITP. Yeah. Okay.
Let's give them a round of applause. And our next speaker is Laura Klaassen. All right, Laura, over to you.